At exactly 5:03 p.m., no one in Japan could have fully prepared themselves for what was about to unfold. The ground beneath their feet suddenly, violently, began to shake. The tremor lasted for a frightening duration, but that wasn't the end of it. Just minutes later, it struck again. The entire nation held its breath as two megaquakes hit nearly back-to-back, sending catastrophic shockwaves from the deep ocean floor straight toward the nation's busiest and most vibrant cities. Emergency sirens immediately began to wail across the coastline. This was not a drill. This was the sound of imminent danger. Coastal towns, whose residents had long shared a close relationship with the sea, were forced to brace themselves, preparing to face a colossal and entirely unpredictable threat. Without delay, official tsunami advisories swept the entire eastern coast, transforming the hope for a peaceful evening into a frantic race against time. But what exactly was it about this rare dual earthquake phenomenon that escalated it into such a terrifying, massive tsunami threat? And how did authorities manage, in mere moments, to accurately decide which regions were in the highest risk zone and required immediate evacuation? The answers are far from simple. They lie deep within the secrets of geological science and in a robust defense system built upon decades of painful experience and meticulous planning. We are about to unpack these critical, life-and-death opening moments, where every single second carried the weight of survival. As the shaking subsided, the Japan Meteorological Agency, or JMA, immediately published their seismic intensity maps. The resulting picture was chillingly clear. The strongest shaking levels, measuring 4 to 5 on the JMA scale, had spread rapidly across the Iwate and Miyagi prefectures, penetrating deep into coastal valleys and small fishing towns. In these areas, buildings were violently rattled, power lines swayed precariously, and a series of automated local alarms triggered an inescapable chain reaction of national warnings. Within just minutes of receiving this verified data, official tsunami advisories were issued for 3 crucial prefectures: Iwate, Miyagi, and Fukushima. This advisory was a non-negotiable directive. It meant that waves up to 1 meter high could strike the coast, and anyone in low-lying areas absolutely must abandon their homes and move to higher ground immediately. A tsunami advisory does not confirm a devastating wave is coming, but it definitively signals the presence of dangerous currents, a severe risk of localized flooding, and the urgent necessity for mass evacuation. Iwate Prefecture, positioned closest to the offshore epicenter, faced the highest level of alert. Neighboring Miyagi, with its extensive coastal exposure, was next in line. Fukushima was also included as a necessary precaution, following the standard protocol required whenever offshore earthquakes of this considerable magnitude are detected. These 3 prefectures, a region scarred by past disasters, once again found themselves as the most tsunami-prone coastline in Japan. The alert system was fully engaged, but the true battle against the ocean's fury was only just beginning. This was the moment where preparation and community vigilance became the most powerful weapons available. While the 3 primary prefectures faced immediate and direct risk, the status of Chiba, Aomori, and Hokkaido remained under intense review. These regions were not part of the initial advisory, yet tide gauges streamed real-time data from along their coastlines. Every minute fluctuation in the water level was logged and tracked meticulously, as a sudden change could rapidly turn a temporary cautionary measure into a full-scale tragedy. By 5:15 p.m., Japan Standard Time, the directive was unambiguous. Urgent evacuation orders echoed through city loudspeakers and were pushed directly to mobile phones within the advisory zones. Maps displayed on every major broadcast and government site instantly highlighted the danger zones in flashing yellow, tracking the advisory's reach in real time. For the residents, the message was crystal clear. Move inland, avoid rivers, and do not, under any circumstances, return until the official all-clear was given. As the alert spread, coastal communities tensed up, bracing for the next phase and watching for any sign that the sea might be rising. But even while citizens were racing against the clock, another safety system, one that was automatic and often unseen, was triggered. The moment the first tremor struck, rail traffic across the entire northeastern region of Japan froze completely. Inside the crucial JR East Japan Railway Company, control center, automated earthquake sensors showed zero hesitation. They triggered an immediate full-scale shutdown of every Shinkansen high-speed train and all local lines operating between Iwate, Miyagi, and Fukushima. System protocols are rigid. They require a complete, instantaneous stop whenever seismic intensity reaches level 4 or higher. Within mere seconds, Hundreds of trains decelerated and coasted to a halt. Some were stopped inside tunnels, while others sat motionless on open tracks. Crew members instantly began safety checks and radioed crucial updates to dispatchers. Passengers waited quietly and calmly in their carriages, strictly adhering to the instructions delivered via the intercom staff. The system left no room for panic or ambiguity. Running parallel to the train stoppage, power grid systems in coastal towns flickered and failed. Utility companies reported temporary blackouts affecting parts of Iwate and Miyagi. Critically, however, backup generators instantly roared to life, powering essential sites like hospitals, evacuation centers, and key train stations while utility crews worked to restore primary service. Streetlights along main roads automatically switched into emergency mode, and traffic signals continued to function using battery backups. These robust safety systems are far from accidental. They are the direct result of years of meticulous planning implemented since previous large-scale disasters. Automated train stops and targeted grid isolation are specifically designed to prevent derailments, catastrophic fires, and cascading system failures. Even after the shaking had fully subsided, JR East teams ran extensive diagnostic checks before they would clear any train to move again. In most affected areas, rail service remained suspended for over 1 hour, with absolute priority given to lines that served primary evacuation routes. Every measure was calculated to buy invaluable, precious time for both the public and the emergency response crews. Movement had ceased, but chaos did not follow. Instead, the engineered systems performed exactly as intended, buying precious time for both the thousands of passengers and the critical emergency crews. As the alerts continued and the initial shock began to subside, the focus of the nation shifted sharply to a deeper question: understanding what exactly had caused such widespread and instantaneous disruption in a matter of minutes. The truth lay in the geological anomaly of the twin ruptures. This pattern is rare, and critically, it behaves vastly differently from the single massive earthquakes that most people remember from recent history. To grasp the severity of today's event, one must recall the devastating 2011 Tohoku earthquake. In that event, a single, enormous rupture tore open nearly 500 kilometers of the Japan Trench in one continuous, overwhelming movement, a magnitude 9, the strongest earthquake ever officially recorded in Japan. That single break unleashed enough unfathomable energy to instantly trigger a catastrophic tsunami that swept across the entire Tohoku coast. The 2004 Indian Ocean earthquake followed a terrifyingly similar pattern, with a single enormous rupture stretching over 1,300 kilometers, creating one of the deadliest tsunamis in modern history. What happened today, however, is definitively not a repeat of those events. Instead of one massive tear, two entirely separate faults slipped almost simultaneously, within minutes of each other. The first registered at a substantial magnitude 7.8, followed almost immediately by the second at magnitude 7.6. This pattern, which geologists term a twin rupture, fundamentally changes the dynamics. It spreads the released energy across a wider area, yes, but crucially, it does so over shorter individual fault lengths. Scientists define each one of these breaks as a rupture, a distinct section of the fault line that suddenly slipped and released its built-up tectonic stress. When these ruptures occur in such close proximity, the resulting seismic shaking can blanket a much broader geographical region, increasing the scale of the immediate damage. But when assessing the true tsunami risk, the shaking intensity is only half the story. The risk depends far more heavily on how much the seafloor actually moved as a direct result of these twin slips. This is why the activation of high-tech geodetic sensors and deep ocean satellite data is now absolutely critical. Experts need to pinpoint exactly where and by how much the Earth's crust shifted before they can confidently confirm the true scale of the imminent tsunami hazard. The traditional models for single rupture events simply do not apply with the same certainty here, leading to a much higher level of anxiety and scientific urgency. The complexity of multiple, simultaneous fault movements means that the potential for displaced water is distributed in an irregular, harder-to-predict fashion. This twin rupture scenario presents a unique and terrifying challenge to Japan's world-leading disaster prediction capabilities. The next few hours will rely heavily on decoding these irregular geological movements beneath the waves. As soon as the Earth stopped shaking, sensor systems across Japan's coastline switched instantly to maximum alert. At the National Research Institute for Earth Science and Disaster Resilience, known as NIED, Scientists immediately began tracking an influx of satellite and ground data, searching for any telltale signs of crucial crustal movement. The key technological tool being deployed for this initial assessment is called INSAR, which stands for Interferometric Synthetic Aperture Radar. This sophisticated system utilizes sequential satellite images to spot incredibly subtle centimeter-level shifts in the ground that are invisible to the naked eye. Following the twin quakes, the very first satellite pass provided preliminary data that revealed an irregular and concerning zone of displacement situated just west of the epicenters. While the full extent of this movement was still under rigorous review, these early patterns held the potential to decode the disaster's true threat. Dr. Takashi Hattori, a leading expert at NIED, explained that these initial displacement patterns are vital. They can quickly signal whether the seafloor has primarily lifted or dropped, a distinction that determines whether the movement was sufficient to drive a massive volume of water outward and generate a destructive tsunami. Simultaneously, tide gauges monitored continuously by the Pacific Tsunami Warning Center began streaming real-time water level data from harbors and coastal stations, especially along the historically vulnerable Sanriku coast. Every single spike or dip recorded in the water level was logged, cross-referenced, and carefully tracked against complex computer model predictions. By the late evening, key coastal tide stations, including the port of Ofunado, remained under extremely close watch. However, in a cautious moment of relief, no official surge readings exceeding the initial advisory levels had yet been published. The scientific community continued their painstaking work, analyzing every line of data and every digital wave trace, searching for any definitive sign that the sea might rise further or suddenly accelerate. The mechanism is well understood. A tsunami forms exclusively when a huge section of the seafloor suddenly lifts or drops, forcefully displacing a massive volume of water outward in all directions. This fundamentally differentiates it from storm surges, which are driven by atmospheric wind and pressure from above. A tsunami is triggered directly and violently by the powerful movement of the Earth itself beneath the ocean. In the highly complex case of these twin earthquakes, scientists are hyper-focused on detecting any evidence that the seafloor shifted enough to truly set a giant wave in motion. If a full-scale tsunami is generated, the critical time it takes to reach the nearest coastline is measured not in hours, but in a mere handful of minutes. For much of the Sanriku coast, the critical expected arrival window is dangerously short, typically between 10 and 30 minutes after the initial fault rupture. The margin for error or hesitation is almost non-existent. The Pacific Tsunami Warning Center's models, meticulously calibrated based on the exact location and calculated size of the twin ruptures, continuously calculate how quickly a potential wave could travel from the offshore epicenters to vulnerable coastal towns like Kuji, Ofunado, and Miyako. Even a relatively small vertical shift of just a few meters on the seafloor has the catastrophic potential to send a wave racing toward the shore at the terrifying speed of a highway vehicle. This terrifying reality is precisely why advisories and evacuation orders are issued before there is any visual or definitive confirmation of an actual surge. The crucial difference between a life-saving warning and devastating impact can often be measured in mere moments. Authorities now faced three possible scenarios, each outcome heavily shaped by the stream of new data and the ongoing official monitoring efforts. The most probable and most likely outcome was predicted to be moderate surges. These would manifest as waves up to 50 centimeters high, powerful enough to generate strong, dangerous currents and cause highly localized flooding, particularly within confined harbors and river mouths. This specific scenario, however, also brought with it the highest probability of repeated aftershocks. Aftershocks are smaller earthquakes that invariably follow a main event, and they can continue to rattle the region for days or even weeks. These are themselves a threat, but they also signal instability. Scientists are acutely aware that if a delayed, secondary slip were to occur along nearby, stressed sections of the trench, tide gauge readings could suddenly and dramatically rise. Such an event would instantly prompt renewed advisories and necessitate a fresh wave of urgent evacuations. In the rarest and most devastating scenario, an undetected or hidden rupture deep beneath the ocean floor could still trigger a highly damaging and unexpected tsunami. As of the current monitoring period, thankfully, no definitive evidence strongly pointed to that rarest scenario. Scientists and dedicated emergency teams maintained their vigil, watching intensely for key trigger signals. These red flags included sudden, inexplicable jumps in the tide gauge data, the formation of new, tight clusters of aftershocks, or clear satellite signs of new, significant land movement. Each of these signs would become a determining factor, helping authorities decide whether existing alerts should be safely lifted, tentatively extended, or drastically escalated. In a proactive response to the advisory, evacuation shelters were swiftly opened in school gymnasiums and civic halls across Iwate, Miyagi, and Fukushima, within just half an hour of the first alert being issued. Volunteer Fire Chief Satoru Endo, for instance, led his dedicated teams through Kugi's darkened streets, personally checking on elderly residents and guiding them firmly toward safety. His experience spoke volumes. He noted that the seniors in his community still vividly remember the trauma of 2011. He said their legs might be slow, but their memories make them fast to move when that siren sounds. Officials and residents were all united in watching for these critical warning signs: the sudden spike in aftershocks, tide gauge readings exceeding 30 centimeters, or any new, dire alerts from the Pacific Tsunami Warning Center. These events represented the immediate red flags for the next 72 hours. Conversely, the green list, the goal was defined by sea levels stabilizing, advisories being downgraded, and no new crustal movement being detected. Prime Minister Fumio Kishida addressed the nation with an urgent, solemn plea, urging all citizens in the affected areas to immediately move away from the coast and to remain fiercely vigilant for any further aftershocks and the possible arrival of secondary tsunami waves. The message was clear. The immediate danger had passed, but the threat was not yet over. The period immediately following a major earthquake is often the most treacherous, as stressed fault lines can continue to adjust. Crucially, deep ocean assessment and reporting of tsunamis, or DART sensors, strategically positioned offshore, continued to feed critical live data back to monitoring centers. This continuous stream of information provided communities with the necessary intelligence to stay highly prepared. This relentless, real-time data flow underscores the single most vital lesson learned from past disasters. Today, Japan's early warning systems turn seconds into survival. These are not mere technological novelties. They are the nation's frontline defense, a comprehensive network designed to minimize the catastrophic window between detection and impact. As seismic patterns globally grow less predictable and more complex, a trend underscored by the very nature of today's twin rupture event, vigilance becomes the nation's non-negotiable requirement. It is the defining characteristic of preparedness in this new, unpredictable era. The combined strength of real-time science, rigorous community drills, and ultra-rapid alerts now stands as the ultimate firewall between potential disaster and national safety. The quiet, disciplined response witnessed in the immediate aftermath of the quakes, the automated train stops, the organized movement to higher ground, the seamless shift to emergency power was not a coincidence. It was the direct, deliberate, and effective execution of a multi-decade national strategy. The resilience displayed, right down to the elderly residents who moved swiftly from memory rather than physical speed, is a testament to this deep societal readiness. In this new and volatile era, a state of preparedness that is continuously tested and proven remains, undeniably, Japan's strongest shield against the formidable, eternal threat posed by the sea. The world watches, not only because of the danger, but because the nation's response offers a definitive, powerful blueprint for survival against nature's fiercest forces.